Nope, nope, yep, okay, I got it. All right. I didn't have the sound for a minute. Okay, let's talk about Newton's method. Okay, Newton's method. This is what Newton did one day. He stayed up all night, he burned up a couple of candles, and he figured out how to find the roots of an equation using derivatives. And that was a pesky question, especially when the root of that equation is an irrational number. He was really trying to estimate irrational numbers to an arbitrary number of decimal place precision, okay? So we're going to be talking about how to do that. So let's do so. Consider the following. Let's say you have a function that looks something like this. Let's make up any old function. All right, so here's my function. And it does craziness, and it has a 0 here. All right? Now, let's say that 0 is between, I don't know, 3 and 4. That's all I know. So to estimate it, I could say 3.5, 3.6, eyeballing it, right? How do you get a better estimate? That's what Newton was after. And as it turns out, he then applied it to roots that were irrational to find, irrational numbers more accurately, okay? So that's really what the idea here is. So what he did was he said, okay, let's pretend that the root is actually 4. Or 3, something easy. You can eyeball, okay? And it's doing that again. Okay, it's between 3 and 4. Let's pretend it's 4. Now that's not really a good answer, right? It's an overestimate, it's not that great. What he then said was, okay, how do you make it better? What if I draw the tangent line there? Let's draw a tangent line there. So at this point, what does the tangent line look like? Let's see, let's use one of these. I don't know, something like this maybe? No, that's not it. No, go away. Okay, something like that. Let's say that's the tangent line. All right, so my first guess is whatever the heck I want. Try to make it close, but something easy, like an integer is fine. But I wasn't happy with that, so now what we do is we try to get the 0 of the tangent line. Now what's nice about that is, look at that 0. It's closer to the actual 0 I'm looking for. All right, so if I call this my initial guess x sub 0, this is my new guess x sub 1. I want to get to this. What? My best guess, let's call it x sub n. I don't know how many times I have to do this to get a good guess, but it's n times, let's say, okay? 5 times, 10 times, 12 times, whatever it is, okay? Somewhere along the line, my guesses are going to get so close to the real answer that they're going to be indistinguishable from that answer. You're going to get like a convergence table kind of an effect, okay? So what we want to do is a recursive method. Recursion, ever hear of recursion? Yeah, you've heard of recursion? Anyone take computer science? Or do any programming in C++ or Pascal or Java or anything nice like that? Okay. We're going to take our initial guess, make a tangent line using the derivative, right? Get the 0 of that tangent line, and if that's no good, guess what you're going to do? You're going to take that point and start over again. You're going to do the same thing over and over and over again. The input to my algorithm the next time is this new 0 here. Here's my first input. Give me a tangent line there. All right, now find the 0 of that. That's my new input. Give me a tangent line there. All right, so let me draw a tangent line along the curve where at x1, what would that look like? I don't know, let's see. Tangent here, something like that. Say, okay. And now what's nice about that? Is that nice? Why is that nice? Because look what the 0 of that tangent line is. It's way closer to the answer I'm looking for. I'm trying to get this. I don't know what it is. But I can get a 0 of a line. That's easy, right? If you say y equals 2x plus 1, is it easy to set it equal to 0, find x? Yeah. And that's what this is going to boil down to, okay? All right, so how are you going to do that? Well, this is how you're going to do it. Remember that you can write the equation of a line this way. Y minus y1 equals m times x minus x1. Now, in the context of this problem, I'm going to say my initial guess was x0. Let's call it x0 and y0. My first point of tangency. All right, so I'm going to put a 0 here and 0 here. Okay? So same difference. It's a point. x0, y0 is a point. M, yeah, that's an M for slope, right? All right, now realize what M is. M, isn't that the derivative there? So I'm going to write that. I'm going to say it's going to be f prime at x0, and y0, isn't that f at x0? So the given function, we're trying to get the roots of it, right? That's f. And my initial guess is x0. And y1, therefore, is f of x0. And the slope, therefore, is f prime at x0. Are we okay? Now, what I want to know is what's my next guess going to be. What's my better guess? x1, right? Now, x1 is the 0 of this tangent line. This is a line. This is the tangent line, right? So when is it 0? When y is 0, I can solve for x1. Okay? So this is going to give me a formula for iterating or recursing over all the tangent lines. Okay? It's an iterative process. Iterative, repetition, repeated. But it's recursive in that the output of this, the answer of this question, what's the root of that tangent line, is the input of my next recursion, the point where I'm going to get the next tangent line, the point of tangency, right? Okay, so how do you solve for x1? Well, simple, because what's 0 minus f of x0? Simply what? Just negative. So get rid of the 0. Okay. How would you get x1 alone? That's my question. I want to solve for x1, my next better guess. Distribute, yeah, it's easier if you don't, I think. What's another way? Yeah, how about we just get rid of this guy? Divide by that, right? Okay, so then I get negative f of x0 divided by f prime of x0 is equal to what's left over here, x1 minus x0. So one more step, how to get x1 alone. That's what I want to know. What's x1? Add x0 to both sides. So what's x1? x1 is x0 minus f of x0 over f prime of x0. Okay, and you could do this by hand. Okay, you could, given some kind of an equation where you're finding the roots, you can pick a nice easy guess for x0 near the root and plug it all in there, and you get x1 a better guess. If you don't like that, plug that answer back in and get another answer. You don't like that? Plug that answer back in, get another answer. In other words, this is the recursion. If x1 isn't good enough, x2 is based on x1. If x2 isn't good enough, x3, a better guess or better answer, is based on x2, doing the exact same procedure. Because we're just going to draw multiple, many tangent lines, is what we're going to do. Okay? Alrighty. Up to where? All the way up? Okay. All right, so we're going to see how this formula works recursively by hand, and then we're going to find that it's very tedious to do by hand. So how about we write a program to do it? Realize that Ziggy, your TI-83, is a programmable calculator, a programmable computer, in fact. It has a programming language built in called TI Basic. Ever hear of BASIC? Beginner's All-Purpose Symbolic Instruction Code. Never heard of BASIC? In fact, it's a special dialect of BASIC, TI Basic. It's a specific dialect of TI Basic, TI-83 Basic. Or 84, it's the same, if you have an 84, okay? So we're going to write a program in a little while. Remember the syllabus, the first thing? Programming your TI-83. That's going to become instrumental here, okay? And we're going to use that program to generate convergence tables, especially if n gets huge. Notice what n is. The number of recursions. 1, 2, 3, 4, 5, how many, right? All right, let's do one by hand. Let's say I gave you y equals x squared minus 2, okay? And this is, in fact, a problem like what Newton was looking for. Because do you realize what the roots of that parabola are? If you set y equal to 0, what's x? Plus or minus rad 2. So if you estimate the roots, at least the positive root of this parabola, you're going to estimate the square root of 2. Right? If you set this equal to 0 to find the x-intercepts, how do you get x along? Add 2, and then square root, and you get a positive and a negative root. Remember, second degree equation should have 2 roots. Why does that make sense? What is that? Because x squared, y equals x squared looks like this. It goes through 0, 0. But what does the minus 2 do to the graph? Translation, right? It translates vertically down. All right, so it looks like, say, like this, where it doesn't go through 0, 0 anymore, it goes through 0, negative 2 for the turning point, right? But this root is rad 2. X equals rad 2 there. This point is rad 2 for x and 0 for y. And this point is negative rad 2 for x and 0 for y. Okay? Now if we graph that, actually graph that on our calculator, we could get a feel for what's a good guess. Remember, we had to want to pick an integer that's close. Do you have any idea where rad 2 falls? Between what 2 integers in your head, do you? Between 1 and 2. But if you didn't know, or if there's some wacky problem you don't know, right? Graph it and see. All right. So let's go into y equals, or, yeah, let's not. Let's not say we did. Turn it on. Okay. All right, so if we graph it, just to get an idea of what's a good first guess, then we can do the rest by hand. So go into y equals and clear out the stuff we did last night, which for some reason I saved the state. I don't know why. And you graph x squared, which we've probably done before. Zoom 4 is probably sufficient. I'm looking for, oops, wrong one. Sorry, x squared minus 2. Okay, so see, it's obvious now that a first guess is 1 or it's 2. I don't care. I mean, you could even guess 3 or 4, okay? Unless you get what's known as a pathological case. There are some functions that fail Newton's method. They're rare and few and far between. If somewhere along the line you get an undefined slope, or you have a periodic function like a sine wave, where the 0 of your tangent line ends up closer to another 0 than the one you want, you might get some kind of chaotic answer going on. Those are pathological cases. Let's not worry about that. But there are some cases where Newton's method fails. Don't worry about it right now. So what, you tell me, what's your first guess? Pick one. 1? Okay, fine. All right, so let's use our rule, which says that x sub n plus, stop doing that, x sub n plus 1, my next guess, is x sub n minus f of x sub n divided by f prime at x sub n. Now, I wrote this in terms of x1 minus f of x1 over x prime of x1 is x2. But I'm saying in general, what if it's not 1? What if it's 3? Then that's 4. What if it's 5? Then that's 6, right? So the 6th guess is based on the 5th answer. All right, so now that's the general rule for Newton's method. So if I ask you to write down Newton's method, there it is. How do we apply it to our function? Well, our function was x squared minus 2, right? So how do you rewrite this? X sub 1 is x sub 0. And remember, you told me x sub 0 is what? 1. All right, so let's write it. It's 1. Well, wait. All right, maybe I shouldn't write it. All right, let me write it more in general. X sub 0 minus. Now, how do I write this in terms of f? Just like we did in the difference quotient when we had to write out f of x plus h, took x plus h and plugged it into f, right? Well, I'm taking x sub n, I'm plugging it into f. What's my f? X squared minus 1. So plug in x sub n and you get, well, in this case, x sub 0. X sub 0 squared minus 2. All right, that's the numerator. Notice it's only this fraction. It's not all a big fat fraction like the difference quotient, right? It's just, this is the fraction. Now, what's f prime? Now, notice I'm not asking you to use the difference quotient definition of the derivative to find x prime. You know how to do it. What's the derivative of x squared minus 2? 2x. Plug in x sub n. And what do you write? 2x sub n, well, in this case, x sub 0 squared. Okay? So that's what I'm going to do. Now, plug in your first guess. You said 1, right? Question? Yeah? Because it's not? Okay. You said 2x, didn't you? Yeah. The derivative of x squared minus 2 is 2x. Okay. All right, so let's plug in our first guess. x1, our next guess, is going to be based on our first guess, and I'm going to guess x0 is 1. So I got 1 minus 1 squared minus 2 over 2 times 1. Okay, that didn't happen, okay? 1 squared minus 2 over 2 times 1. All right, so let's evaluate that. 1 squared is 1, minus 2, negative 1, over 2 times 1, so negative 1 over 2. Subtract a negative 1 over 2, you're adding 1 half. So what's the answer? 1.5, 1 and a half, 3 halves? How about 3 halves? All right, so that's my next guess. Is that any good? Well, go back to the graph. My first guess was 1. My next guess is 1 and a half. It is, I think, closer than I was to the real answer. The real answer being whatever the heck that is, right? So I started at 1. My next guess is 1 and a half. Is that good enough? Well, no, because think of it. If you draw this as a convergence table, you're going to have 1.0000 fixed 4. Remember fixed 4? 1.0000 is my first guess. Then 1.500 is my next guess. I don't have a lot of convergence going on, right? Keep on going. So probably I want to write this as a decimal. I probably want to do that. But all right, keep it going. Let's do it again. What's x sub 2? X sub 2 is x sub 1 minus x sub 1 squared minus 2 over 2 times x sub 1. I'm just plugging in my new guess where I had my original, the 1s, right? And let's work that out. Okay. That's 3 halves minus. Now what's 3 halves squared? Well, I'm going to use fractions to do it in my head. I'm not using the calculator until I have to. We're going to do that. But well, improper. 9/4. Let's make it easy. 9/4. Okay, so I want 9/4 minus, I need a common denominator. This is 2 over 1. What is it in fourths? 8/4. So I got 9/4 minus 8/4 over, well, what's 2 times 3 halves? 6 halves, because that's really 2 over 1 times 3 over 2, multiply across. Numerator times numerator, denominator times denominator, 6 halves. And what is this difference up here? You could, but I'm being more general. You want to make it 3? You could do that. Or 3 over 1 if you like. I'm going to have to divide by it, so I need the reciprocal. I need a fraction, okay? Anyway, what is this? 1/4? Okay, so this is going to be 3 halves minus 1/4 over 3 over 1 if you like, right? 6 halves is 3. But I need a fraction here. Why? Multiply the reciprocal, 1/3 instead. Okay. And so what is that product? 1/12. Okay. So I got 3 halves minus a 12th. How do you subtract fractions without common denominators? You need a common denominator, right? What is it? How much? 12. So 18 twelfths? Okay. So I got 18 twelfths, multiply top and bottom by 6 to get the common denominator of 12 on the bottom. So 18 twelfths minus 1/12 is 17 twelfths. And now it's already getting really, really tedious as to what the hell did I just get? Did I get a better answer? Is it converging or not? I want to use some decimals now. I want the calculator to do this for me over and over and over. Okay? So let's let the calculator do it. First, let's figure out how are you going to write it in Ziggy's. Okay? How do you write this on the calculator? And then how do you automate it as a program? Okay? So, 17/12, what the heck is that? Well, that's 1 and 5/12, right? And 5/12 is a little bit less than 6/12, a little bit less than a half, so 1.46 something maybe, I don't know. 416 something, okay. So that's even better, that's even closer to my answer, but it's hard to tell. It's, you know, so let's make a convergence table in the calculator. Let's try and figure out how to do this as a program, okay? So here we go. So that's enough scratch paperwork. I don't feel like doing this anymore. I need a pointer, I need a calculator. Let's do this on Ziggy. Oh, Ziggy, wake up. Why do you keep on going to sleep? Ziggy is on vacation this summer, I guess. I don't know. Okay. So, all right, so you're going to want in Y1, let's say in Y1 you're going to put the function you're trying to get the zeros of, okay? All right, fine. And then what I want to do, whoops, clear. What I want to do is write that formula, this formula here. I want to figure out, for a particular x value, x minus f of x, but where's f of x now? Where did I store it? Y1. So it's not f of x, it's y1. Remember, Ziggy uses functional notation. Y1 of x is like f of x. I'm plugging in stuff, right? So I need x minus y1 of x divided by what? How do you get the derivative on the calculator again? Math 8, and derive, numerical derivative, right? If you were to take the AP exam in AB calculus or BC calculus, they tell you that whatever calculator you use has to have 5 properties. 1, no QWERTY keyboard. We talked about that, right? You have to be able to draw a graph, an arbitrary graph, a complete friendly window, that kind of stuff, right? You have to be able to find roots of a function, find the roots of a graph. You have to be able to do a numerical derivative and a numerical integral. We'll talk about what that is later. But these 3 you should know how to do already. Find a graph, an arbitrary graph, a friendly window, a complete window, that kind of stuff, right? Finding the zeros of a function on your calculator, finding the numerical derivative of a function on a calculator. You can do these things, can you not? In fact, if I go back to this, and I said, forget Newton's method for a minute. How do you find the zeros of that thing right now? Let's cut to the chase and see what the answer is. We'll cheat. Can we get the answer right now in this graph screen? How? Tracing is not accurate enough. Because unless you have a friendly window where your trace is going to hit the 0 exactly, right? It's not going to let me get y equal to 0 exactly here, right? Forget it. Trace is no good. What's better? Second trace is calculate, and in there you got 0. Okay, so you can find the 0 of any equation that way, or you can solve equations this way. Now what I'm going to do is I'm going to take a left bound such that my y value is negative, and a right bound such that my y value is positive, because I'm assured in a continuous function that therefore there's a 0 somewhere in between. That's called the intermediate value theorem in calculus. We didn't get to that yet. And you don't have to guess. And the 0, when y is 0, is at 1.414 something. Now remember, this is in fixed 4, so it's rounding off the 4th place. So I'm not trusting the 2. But 1.414, it should be in my answer when I'm done. Okay? All right. So you know how to graph. You know how to get the zeros on the graph. And you know how to get the numerical derivatives along the graph. You can even do it here. Second Calc 6 at whatever point you feel like, you can get the derivative of the function if you want, right? Numerically, right? Okay, so we're going to do that. So what I want to do is I want to do x minus y1 of x divided by math 8 of y1 with respect to x with, hello, lost my pointer. Wake up. That's not good. What is that? With respect to x at a particular x value. Wait, let me see if I got my syntax correct. My bestseller on eBay. What? Y1. Vars, y vars, function 1. Vars, y bars function 1. Okay. Do you need any parentheses around what? Where? You want a parentheses here? In front of the y1. After the y1.
First, x minus y1.
Yeah. Yeah, but remember your order of operations is going to divide before it subtracts anyway. So that's optional, what you're saying. Yeah, I don't like to write optional parentheses if I don't have to, because very often you get messed up if you have too much stuff on the screen. Yeah, so I'll avoid that. Okay. By the way, this is my bestseller on eBay. I sell hundreds of copies of this thing every single year on eBay. It's ridiculous. How to program your calculator for calculus class, basically. That's what this is. Okay, so look it up on eBay. It's there. 25 bucks. Let's see, Newton's method, right? CI83. Let's see. Yeah, okay. See, that's what I was worried about. This x and this x are different. This x is the guess that you're making, right? Like the initial guess was 1, I'm plugging in. I have to make a distinction between these two x's. So I'm not going to call it x, okay? Sue me. I'm going to call it g for guess. Now notice how this is convenient. It's not always convenient. It's in type over mode, right? So don't do second delete as insert like we did yesterday when we were adding stuff. I'm writing over. So I need alpha g. Boom. There. I need alpha g here. And I need alpha g here. Because remember that n deriv of y1 comma x is shorthand for dy dx. And then this is where the x value you're plugging into, right? F prime of what, right? So I'm just reminding myself that was a big problem. Yes, it was. Okay, so I'm good. Okay. Alrighty. So that's what I'm evaluating. But remember, if I just hit enter here, what's it going to do? Damn you. That's bad. It divided by 0. Why? Where's the 0 coming from? Apparently, the derivative is 0 at g, because I didn't say what g was. Who knows what g is? Now, remember, it's parabolic, right? Where is the derivative of 0? On the bottom, when x equals 0. Apparently, g is right now 0. Is that true? Let's see. What if wait, enter. All right, so quit. All right, let me quit that. What if I say alpha g, just to see what's in alpha g right now? It's 0. That's why I got an illegal answer. Did you get an illegal answer? I don't know. Does it automatically set variables to 0 before you use them? That's another issue, maybe. Okay, so what I need to do is I need to take 1 and store it as alpha g. Remember that was my first guess? And then I have to evaluate that line. So let's do a second enter, second enter, second enter, until I get that stupid line back. Okay. And now I get 1.5. And remember, wasn't that my next guess when I did it by hand? I got 3 halves, right? Okay, now the next guess was 17 12ths, 1.416, right? Let's see if we get that. All right, now let's make that our next guess. Let's say store that answer, 1.5, as alpha g, and then second enter until you get that line, and evaluate it with that g, 1.5. And you're getting the 1.416 thing. And remember, the answer, we cheated, right? You ever hear the Galloping Gourmet? Yes. He always cheated, right? What was his hallmark? He was like a Julia Child. You know Julia Child? You ever see that movie Julie and Julia recently? You know Julia Child, right? This was another guy like Julia Child. It was a man, Julia Child. His name was, I forget his real name, the Galloping Gourmet. And he had a half-hour show on TV. Graham Kerr, whatever. Yeah, and he would do these insane, massive, roasts and stews, things that take like days, right? And he had to show you how to do it in half an hour. So he cheated. he would spend, like 20 minutes showing you how to mix the ingredients and blah, 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 and throw it in the oven. But he'd throw it in this oven, and then he'd open up this oven. Well, yeah, I did it 3 hours ago, and it's done. Ta-da! And then he'd invite somebody from the audience to eat with him, and it was so delicious. We did that. We just did calculus a la Galvin Gourmet. We know the answer, don't we? 1.414. We know that's getting better. How do we make it even better? Store that as G, and do it again. All right, so let's see. Store that answer. That automatically comes up when you hit store, okay? So it'll take the previous answer, and let's store that as alpha G, and then reevaluate that, second enter, and now we're getting the 4142. Now remember, the 2 we weren't too happy with. There was probably round-off error there. I don't even know exactly what the answer is. If I could change the fix from 4 to 10 or something, I could make this converge to as many places as I feel like. But I have a feeling that if I do it one more time, I'm done. Remember, when are you done with a convergence table? When all the digits match. But remember, the last digit is problematic. You don't know if if there's round-off error in there, so we don't include it as part of our answer. I would say the answer is 1.414 if it matches now. Yeah.
At 1.5, what do you do then?
At 1.5, I just hit store.
Right.
Store, and then alpha, G, enter, and then hit second enter a bunch of times until you get this line again, and then hit enter there, and it'll reevaluate with 1.5.
All
right, well, we'll unscrew it up in a minute. All right, so let me do it. Let's see. Store in alpha G, that previous answer, and then second enter, whoops, and enter. And there you go. There's the convergence. You want to see it even easier than that? Let's start this again, okay? This is what I'm going to do. I'm going to say, look, I'm going to start all over again. In fact, I'm going to start with a different initial guess. Wasn't 2 good, 2? Let's do 2. All right. So how about I do 2, store as alpha G. I'm doing the same problem over again, right? But now I'm starting at 2 instead of 1. And then I'm going to do this. Look at what I'm doing. Second enter, but I'm going to make it automatically store that as the new G for me, so I don't have to do that storing stuff every time. And, ready? Are you ready? Here's your convergence table. Enter, boom. All right, now that we know how to write this in Ziggy-Ease, let's write a program to do it for us so we don't forget ever how to do this. It'll be stored as a program on your calculator. You can use it whenever you want. Realize we did this already. When we went on the graph and we asked for second calc 0, and we asked it to find the zeros, guess what Ziggy was doing? Ziggy was doing Newton's method. Okay? But I need you to know how Newton's method works for tomorrow, okay? There's going to be a question, at least one question, specific about Newton's method. So what's Newton's method? A way of finding zeros of a function. Why is Newton's method historically important? Because it's a nice way to find irrational numbers, estimates for irrational numbers. You're going to use the program on your calculator. Yeah. Mm-hmm. Make sure this program is running. I'm going to write it right now with you. It'll tell you what to write down. It'll tell you to write down Newton's method in general, write down Newton's method in terms of this function, then write down a convergence table or something like that. It'll tell you what to do. All right, my word problems are very step by step. Step A, do this. Step B, do that. Step C, just do it one step at a time. You'll get to the answer. It's okay. It's sort of an exploratory problems, okay? Yeah.
How did you get it to say in a row 1.5?
Because I changed the line. At the end, I didn't have, originally when I first did this, I didn't have store G at the end. So not only does it calculate the answer, it stores it as the new G, so that if you hit enter, it's running this again with the new G. And then it stored it again, the new G, and then you run it again with the new G. And if you hit enter, look, it's not changing after that, right? It won't change. So once it converges, you're done, yeah? All right, I'm going to make a totally random guess. Well, okay, not random. remember there were two roots, right? There was rad 2 and there was negative rad 2. So what's near negative rad 2? Negative 4. I don't know. Whatever. Right? So I'm going to pick negative 4 and I'm going to estimate negative rad 2. Let's see if it works. Okay? So here we go. Negative 4. Store as alpha G. And then second enter gives me the line I want. Now, originally I didn't have this part. This is your question. Originally I didn't have this part where it calculates the answer, displays the answer, and that was it. But now I also have it store it as G. So that if I run this line again, it's stored as G already, the new number. All right, so if I hit enter, I'm going to get closer to negative 1.414, hopefully, right? So let's see. And if I hit enter, it's just going to run the same line. But now G was updated. And G was updated. And G was updated. And G was updated. And I'm done. And that's what you write. That's a convergence table. You write that down on your paper. Yeah.
First question is, how do you introduce the arrow with the G?
The store key, it's down here. Right above the on key. Can you see down there? You got it? Okay. All right. So how do you write this answer down? Let's say this was a test question, okay? All right. Let's go over here. Get to a new page. All right. So here's the question. Find the positive root of f of x equals x squared minus 2. And if I don't tell you the precision is fix 4. All right? If I tell you, if I want more than that, I'll say use fix 6 or fix 10 or something. That just gives you more decimals when you're done, okay, that are accurate. All right? So what do you do? Okay, it's going to say, I'm not going to write all of it because it's really hard to write. I'm going to say part A. What's Newton's method? What's the formula for Newton's method? Part A. All right, so what would you write? x1 or x sub n plus 1 equals x0 or x sub n, what? Minus f of x0 over f prime at x0. Okay, that was part A. Part B, rewrite this recursive formula in terms of the given function. Okay, so I would write x1 equals x0 minus x0 squared minus 2 over 2x0. Okay. Part C. Use Newton's method to estimate this root. Provide a complete convergence table. All right? So this is it. If I remember the numbers correctly, after you run the iteration, you don't need a program for this. I'm going to write a program for you to, to show you how to do programs because we're going to need to do programming later. But you notice I did this without writing a program. But it's nice to store this result as a program. So
Part C is one program.
part C is basically run the program. Right. All right, so for different values of n, what's x sub n? X sub 0 is your initial guess. Remember when we did 1? X sub 1 was what? 1 point, remember? 5000, right? Remember, unless I tell you different, just do fix 4 and state the answer accurate to 3 places. Okay? All right, what's x sub 2 then? Well, that was that 17/12, right? Wasn't that 1.4167 or something, right? And then x sub 3 was already the answer, wasn't it? I think it was 1.4142 already. Okay? But are you done? See, if you never did this before, you're running the program, you don't know that it's done yet because I have units place convergence, I have tenths place convergence, I have hundredths place convergence, but I don't have any other convergence. I don't know if I'm done yet. But now x sub 4 turned out to be the same. So I have 4 place convergence. The 4th place may have round-off error, so I have 3 place accuracy. So you have to restate the answer. Rad 2 is approximately what? 1.414. You don't state the 2 because that's not probably part of the answer. If you actually were able to write down Rad 2 forever, millions and millions and millions of digits, right? I don't know about the 2, but it's going to start 1.414. It's got to start that way. Those numbers are not going to change. They're in stone. Okay? The 2, I don't know. You want to figure out the 2, then make it fix 6 and redo the table. Or fix 10 or something, right? All right, so is that terrible? Yeah. Which calculator is this? Really? What's different about it?
Instead of it coming up as n derivative and then coming up y dx.
Let me see this, because I've done this with the 84 too. Were you able to get the answer we were talking about?
I can follow it and see what
Oh, you have the new 84 that uses the pretty print stuff. Oh, God. Yeah, this isn't the standard 84. This is the newfangled 84. Yeah. So you know what? RTFM?
what does RTFM
Read the frickin' manual. Okay, yeah?
I did it before and it worked.
Yeah, but he has a newer model that, yeah, what did you have? Let me see what you had.
Well, I listed, I don't know why.
That. Yeah, hers still has the end deriv. You don't have end deriv?
I don't know if I can change the formatting or not.
Yeah, there's a way to do it. I just haven't used this calculator, this version of the calculator.
so I
Okay.
can input the conditions?
Yeah, math. End deriv is there, but it goes into that format, huh? Y1. Wait, quit. Ooh. So it changes. It's not even the home screen, is it? It's like a whole derivative screen.
No, why?
Is there a way to just use end deriv? Maybe a mode. A way to change the mode to use numerical. Auto answers? Nah. Classic. Maybe classic. Yeah, use classic, okay? All right, if anyone else is getting really weird notation when they do Math 8 on the 84, go to Mode and highlight Classic. Instead of what? Is Classic as opposed to what?
As opposed to math print. As opposed to
Pretty
math.
print or Math print? Yeah. There's a thing in Mode, if the newest 84s are weird, okay? There's a thing in Mode on the second page. It says Math print or Classic. Use Classic. Just highlight Classic. Okay, so let's take a look at some sample questions from the homework. All right? Where you're going to use the program, basically. Yeah. Well, we're going to write the program. Yeah. Okay. You want to write the program? Okay. Let's write the program. Let's write the program. You don't really need the program for this, but all right. I just like to have it in front of me here. Okay. All right. All right. Let's write a program to do the same problem. Okay. All right. Well, let's do a different problem. Let's say, for some strange reason, I need the cube root of 12. Can you name a function whose root is the cube root of 12? What would f of x have to be so that its 0 is the cube root of 12? X cubed minus 12. Cube root of 12. Cube root, yeah. Okay, do you see that? If you solve that, if you set f of x equal to 0, and you solve, what do? You add 12, and then you cube root. So you get the answer is the cube root of 12. All right, so if I want the fifth root of 2, I would put a 5 here and a 2 there. If I want the 10th root of 6, I would put a 10 here and a 6 there. Do you see the game? This is the game that Newton played to get irrational numbers. Okay? All right, so I want this root, which is going to be the cube root of 12. Whatever the hell it is, do you know what it is? I don't know what it is. I knew that rad 2 was somewhere around 1.4 something, right? Cube root of 12? Ugh, I don't know. Whatever. So let's do it, okay? So how are we going to do this? We're going to let's use a program to do this. But now, all right, let's let's go to program mode. Here we go. Go to program mode. And of course, Ziggy's on vacation again. Stupid Ziggy. Stupid Ziggy, wake up. Okay. All right, so go, see where it says PRGM, program? Go to program. Okay? And I don't have Newton here, right? Okay, good. All right, so what I need to do is make a new program. Did you hit program? Did you get something that says exec, edit, and new? Okay, go to new, hit enter, and give it a name. I'm going to call it Newt, short for Newton's method, right? Newt. And notice you're in alpha mode, so don't hit alpha. Now you got to hunt and peck. N, E, where the freak is W, T, where are you? I hate this keyboard. Okay, enter. Now you can write your program. Okay? All right, the first thing I need to do in my program is to ask the user for the initial guess, G. And I'm going to also ask the user how many times you want to do this. How many lines do you want in your convergence table? The first time you run it, just sort of guess, 3, 4, 5, whatever, okay? So the way to get input, has anyone ever programmed anything before? No? C, C++, Java, Pascal, Basic, COBOL, APL? No? Yes? Okay. All programs have 3 things in common. They have to have some sort of, any idea? Input, some sort of way to output, but there's something you got to do in between. Calculate or process that output, okay? So there are standard commands in BASIC for input, there's standard commands in BASIC for output, and there's standard processing commands in TI BASIC that involves all this calculus stuff we got, okay? So I'm going to go and hit program again, but now it gives you a menu of basic commands. There are control functions, there are I/O, input-output functions, and other stuff. I want to do input, but I'm going to use this one, prompt, because it's easy to use, okay? So I'm going to prompt the user for alpha G, the guess. So what happens is when you run this program and it hits this line, prompt G, it just stops and prints on the screen, G equals what? It's asking you, the user, the question. G equals what, question mark, and you type in your G, enter. And then it continues the program after that. But I also want to ask for how many iterations or how many recursions, right? So I'm going to say comma, let's say alpha n. N for the number of times I'm going to run this. Where's n? There's n. All right? So that's a nice, easy way to do input, to get input from the user. Okay? And just hit enter for the next line, right? Okay? All right. If that colon prompt means a new line in your program. All righty. All right, now what I'm going to do is I'm going to do what's called a for loop. We want to do something over and over and over again. In programming, most high-level languages, that's called a loop construct, okay? And the easiest for a loop I'm going to encounter here is a for loop, all right? You ready? Do a for loop. Hit program, again, but now I'm going to use the control command called for, which is conveniently numbered 4. All right, and what am I going to do? Now, what a for loop does is just count how many times you did stuff. So I need a dummy variable, a counting variable. I'm going to call it I. So alpha I, comma, start counting at 2, and go until you hit n, and count by 1. All right, so if you tell that n is like 5 iterations, it's going to start with n, I is 2, do stuff, then I is 3, because it's counting by 1. It's adding 1 every time. You could change this to -1 to count down, to 2 to count by 2s, right? So it's going to start at 2, then it's going to be 3, then it's going to be 4, then it's going to be 5, and it's going to stop. As soon as it hits 6, it knows that's to don't do stuff, stop. All right, so whatever I put after the for line gets repeated until I hit something called the, well, it's usually the next line, but in this dialect, it's the end command. So think of for and end sort of like a paragraph, a block of code. What's inside for and end is sort of like braces. And in there, whatever I type in there gets repeated over and over and over again. And that's the formula we wrote before. And it's just going to type out the answer over and over and over again, okay? So here we go. So hit enter. And what I want to do is write that humongous line I had a minute ago, right? So here we go. Alpha G minus, and the precondition to this program, before you run this program, you have to do what? You have to put something in Y1, right? You have to put the function in Y1 before you run the program, okay. That's called a precondition. All right, so I need Y1, vars, yvars, function 1, open parentheses, add alpha G, divided by the numerical derivative, math 8 of y1, vars, y vars, function 1, at, with respect to x, at alpha g. Okay? And I want to store that as my new g, store alpha g. This is the exact same line we had, right? So, but what I'm doing here is I'm sort of storing this for posterity. You never lose this. It's stored as a program, all right? And I think it'll just display it automatically at that point, like it did before. So that's all I'm going to do right now. And I'm going to hit end. I'm going to do program, end. Okay? And, all right, let's see how that works. I have a very much more complicated version of this thing, which actually draws the tangent lines and all kinds of... Let's keep it simple, stupid, okay? Yeah. End is program 7. Hit program and then 7. Did you see program then 7 is end, right?
No, not end.
End, math 8. Math 8, like we did before on the home screen. All right, so let's test this. Let's test this with the function we had, x squared minus 2, and see if we get the same result. And then we'll use it on our new function, the cube root of, that gets the cube root of 12, right? Okay, so what you do here is you second quit. The program is automatically saved. It's a file in the operating system. It's saved. You don't have to hit save or anything, okay? So if you hit program, notice you have a new program called Newt. You probably had nothing here. Now all you have is Newt, right? All right, so I guess you hit 1. Are you going to hit 1, I guess? Hit whatever number is in front of Newt. If you have other programs from other classes, maybe, I don't know. I hit the wrong one, damn it. Second quit, no. No, I don't want that. Go away. Program, and I thought I hit 4. There it goes, okay. Hit enter, and look what it does. It asks for G. Now, remember, y1 is still what? X squared minus 2. So what's a good G? 1? Okay, fine. So hit 1. And now, let's say we never did this before. How many times do you want it to get a new guess? 5 times? Okay. 5. And done. Okay, so in program mode, as it does the calculations, it doesn't actually display them. You have to do the output. Remember, we did input, prompt. We did process, the for loop with the formula. We didn't do output. Okay, so we got to fix it. Go to program. But now you want to edit Newt. Okay? And what do we want to do? We want to go here at the beginning of the last line, right on the E, do a second insert enter to get a blank line. It gives you a new line, a blank line. We're inserting a new command. And that's what I forgot. What did I forget? Program, IO, display, G. Okay, let me undo all of this stuff. Okay, go to the first character of the line you want to move down. And then you do second delete is insert and hit enter as many times as you need a blank line. I just needed 1. And then go up there, up arrow to there, and I'm going to do program, IO, 3 for display. And what am I displaying? Alpha G. So every time this loop iterates, it'll print out a new answer. It's not printing out the first one. X sub 1, let's say, is my first guess, so X sub 2 it'll print out. Okay. All right, so quit this. It's automatically saved, and run it again. My guess was 1, and I'm doing 5 iterations. And there's your convergence table done. Okay? Are we good? Now you can make it more fancy. You can actually make it print out the convergence table. 1, that, 2, that, 3. And then after that, you can actually have it print out, graph the tangent lines and see how the zeros of the tangent lines get closer. I don't want to get very complicated at this point. And no, you don't need to do that. You may have to draw a line. It's not going to kill you. Maybe 1 or 2. Yeah, not like 5 million of them. All right, there you go. So now let's use our program and do the new question. The new question is this. All right? Now, so what's the first thing you got to do if you have a new question for Newton's method? Put it in Y1 and graph it so you can get a guess, right? You got to see where a good guess is. Then run the program, right? Okay. Alrighty, let's do it. Here we go. So go to y1, go to y equals and change y1. And let's say it's x cubed minus 12. And let's do a zoom 4. And this cubic has one root near what? What's your guess? 2. Okay. It's 2 point, I don't know, I'm going to guess 2.2 something. I don't know. Probably not. All right, so quit that and hit program and choose the program. Hit enter. And your first guess was? 2. How many iterations do you want? 5? Okay. Did it converge, or do you need to run it again for more than 5? There it did. It converged. Good. All right. Now, what if it goes off the screen before it converges? Then run it for like 4 or 5 or something. Copy that down. Then run it for, more. And then copy the rest down. You're basically, to do the convergence table on your paper, you're just copying stuff. That's it. No, not by hand way, no. Maybe like one step. But if it's a lot of steps, this is going to do it, okay? You know how to you have to know Newton's equation in general. You need to know how to rewrite it for this function. Then you need to know how to apply the formula, Okay, so now does that make sense? How do you know if that's right? Well, that's my alpha g, right? If I type alpha g, there's my answer, right? Now that's supposed to be the cube root of 12. So how do I check it? That's cube it, and you should get something near 12. Now remember, this is an estimate. It's not exact. So it may not be 12, but close. Okay. So cube it. Damn good. Right? Okay. So now remember how you write the convergence table, though. You got to write your first guess. Notice this didn't print out the first guess, right? If I run the program again, program, newt, enter, 2, enter, 5, enter. All right, notice it didn't print the 2 at the beginning, right? You do that. The first thing in your convergence table is your first guess, so I know what your first guess is. I need to see it, right? So that's not the convergence table. The convergence table would have one more line with 2.000, right? And I would usually put n and x sub n headers, and n is 1, 2, 3, 4, 5, or 0, 1, 2, 3, 4, whatever you want to call it. The way this program runs, x sub 1 is your initial guess, because it started at n equals 2, remember? So it's really arbitrary what you call the first one. You could call it x0, x1, really arbitrary. Yeah. That's what I was just saying. It's skipping 1. 1 was the guess. Okay? And when I originally did this on paper, I called that x sub 0, but for some reason I decided in this program to call it x sub 1. Big deal. Yeah.
So if your for loop started at 1, it would give you 2 in the answer?
No, it would just call that first answer x sub 1. It would, in fact, what it would end up doing is give you more iterations than you asked for. Because I'm counting the first one as one of them, the guess. So notice it's giving you 4. If you're doing 5, you should have 5 numbers, right? X sub 1 is your guess. S sub 2 is that one, the first number. S sub 3, 4, and 5. That's it. Okay? Is this clear for everybody? Are we okay? It's your responsibility to get your contraption to work. If you don't know how to use your calculator, RTFM. I'm trying to KISS. I'm talking like a computer science teacher, sorry. The first 2 maxims in AP Computer Science are KISS and RTFM. Keep it simple, stupid. And when you screw up, read the freaking manual, except it's not freaking. Okay? Otherwise, you're liable to run into a snafu. Situation normal, all effed up. Because you foobarred your program. Effed up beyond all recognition, right? These are all computer science terms, sorry. I tend to be computer sciencey when I write programs. That's what I do. Huh?
The G stands for the X.
The initial guess for X, yeah.
And what about the N? What does the N
N is how many times you're going to make the calculator guess. Right? G is your first guess is G, and then it's going to keep on changing G. Right? Okay, did it finish? It's almost finished. We got, what, 12 seconds left? Bye-bye, YouTube. Everyone say bye, YouTube. Come on. Bye, YouTube. Have a nice day. We're done. That's basically 2.6 or appendix